Okay, today we're going to look at operations between vectors. In our previous unit, we looked at adding vectors, subtracting vectors, linear combinations of vectors, scalar multiples. Today we're going to look at how we multiply two vectors together. In this case, we call this the dot product. When you use a dot product, when you multiply two vectors, you actually produce a scalar value. So no more vector anymore, just a single number that represents the size of that thing. Okay. Whenever we're using dot product, we think about our two vectors tail to tail, and their angle is always going to be between 0 and 180. Once you get past 180, if you stop and think about that, for example, I had this one and this one, that's past 180 degrees. Well, it makes more sense to go back to the idea of between 0 and 180. So if we want to find the dot product, when we think of this dot here as multiplying, that's what it really symbolizes. What we need to do is take the magnitude of A and the magnitude of B and the cos of the angle between them and multiply that all together. Now create us our new scalar value. Okay? Because they're magnitudes, that means they're scalars, so it's a scalar times another scalar, hence the reason we produce a scalar answer. There are three different types of scalar values you can get. You can get a positive scalar value if your angle is acute, that's the 90. You can get a negative scalar value if you have an obtuse angle greater than 90. And you can get 0 if your vectors are actually at a right angle to one another. That's kind of a key one we'll talk about a lot later on. If we have perpendicular vectors, 90 degrees to one another, always comes out to 0 dot product. Okay, so some basic things to warm up. I want to find the A dot B. So A dot B is the magnitude of A times the magnitude of B times the cos of your angle between them. In this case, 10 times 15 times cos 50. And we're thinking about cos 50 being an acute angle. So common sense tells us my answer should be positive. And if we put that in our calculator, we get 96.4. So indeed it works. Try the next one. Same idea. A dot B, 9 times 6 times the cos of 120. And cos 120, that tells me it's an obtuse angle. I should end up with a negative, and indeed, in my calculator, it comes up to negative 27. And if I try the third one, hopefully got the hang of this by now. A dot B is 8 times 4 times the cos of 0. 0 is acute. It's cos of 0 actually comes out to the number 1. So 8 times 4 is 32. It's a positive answer, like it tells me it should be. The last one actually wants us to find the angle. They're giving us some information. They're telling us our A dot B. So if I go to talk about that equation there, okay, I can solve other parts of this if I know certain information. I know the dot product's negative 3. It tells me my angle, it's got to be obtuse. I know the magnitude's 1, the magnitude's 5, and I got a cos theta. Well, I can solve that if I multiply the right-hand side. I get 5 cos theta. Or divide it out. I'm going to take an inverse. And I type that in my calculator there, and I get 127 degrees, which makes sense because my angle is greater than 180. It's greater than 90. It's obtuse, and there's a negative dot product. And that's really how we calculate geometric dot products. Two magnitudes and an angle between them. Now, we don't always want to stick with geometric things. Sometimes we want to talk about algebraic things. To do that, there's some properties we need to discuss. Okay? The first one is, if you take the dot product of a vector and itself, well, because the angle between a vector and itself is 0, you end up with a cos of 0, which we talked about in the previous one there. It always comes out to 1. So a vector in itself, their dot product.
Would Mr. Bain please contact the office? Mr. Bain?
The dot product of a vector in itself always comes out to a vector's magnitude squared, right? A vector times cos 0. It's the same thing as the vector squared. Because we're multiplying scalars, order doesn't matter. A dot B is the same as B dot A. We can use the distributive property. We can add vectors first and then take a dot product, or we can take the dot product and then add two things together. We can have scalar multiplication happen. We can do it first and then take a dot product, or we can take a dot product first and then multiply by the scalar afterwards. And we can also do things with unit vectors. The nice thing about unit vectors, like I, is they have a value of 1, right? So if I think about dot product of an I and itself, and I got the idea of 1 times the cos of itself, so cos of 0, that always comes up to 1. And so if we ever come across an I dot I or a J dot J or a K dot K, well, it's going to come out to 1 every single time. So some operations, some algebraic things we can do with this. Example number 3 there in your books. A and B are unit vectors, kind of a key. It tells me they have a magnitude of 1. I know, in other words, that A equals 1. I know B equals 1. And they have an angle of 60 degrees between them. So if they're tail to tail, I know it's got to be a 60. All this kind of information we're getting. I want to calculate this algebraic expression. Well, we've said in the past that we can do algebra with vectors the exact same way we do algebra with algebra. So this kind of looks like, and really acts the same as, doing FOIL. So I can do 7a dot 3a, and that comes out to 21a dot a. The numbers go together and the letters dot product themselves. Okay, if I do the outsides, I get 7a dot b. The insides, I get 3 minus 3. And I get b dot a, or, because order doesn't matter, just write it as a dot b. And if I do the last parts, just good old FOIL, I get b dot b. Now that looks messier because they have all these dots in there, but there's some things we can do with dots. We know a dot a is the same as the magnitude of a squared. And whenever we have a dot product times itself, it always comes out to the magnitude squared. I can collect a dot b's, and I'll get 4 of them. And just these two things together here. And at the end, I've got this b dot b, which means I have b squared. So we've made it somewhat simpler. Now we can go back to this ideas of this stuff up here. What do I know about a dot a? Well, that was the magnitude squared, and we know the magnitude of a is just 1. So it's 1 squared. And same thing over here. B is 1 squared. And what do I know about 4 and a dot b? Well, a dot b is the same as a dot b dot the cos of our angle between them, right? So I can write this out as, well, 21 times 1 squared is just 21. A is 1, B is 1, cos of 60, and this number over here is 1. So I got 21 plus 4 times 1 times cos 60, that makes 2, minus 1 at the end gives us 22. So I can combine algebraic operations with dot products and geometric vectors and produce new scalar values. Take a look at the last one. I've got two vectors again, scalar multiples of each other. They are perpendicular. I'm told they're perpendicular. I'm also told that the magnitude of A is equal to 2 times the magnitude of B. And I want to figure out the angle between A and B if I had this original two vectors. Now the key here is that these things are perpendicular. Because when things are perpendicular, that means the dot product by rule comes out to 0. Anytime I get an angle of 90, the dot product is 0. So I can write that into a formula, if you will. A plus 3b dot 4a minus b has to be 0. There's no choice on that. Because it's an equation, I should be able to solve this, and I can do it by using some of the previous things we just talked about. So let's do our FOIL. So 4a dot a minus a dot b plus 12a dot b minus 3b dot b comes out to 0. We know a dot a is the same thing as a squared. We know we can collect in the middle here like we did before. And we know b dot b is b squared. And we sort of simplify this. Now, we also know that every time we see an a, I can replace it with a 2b. So I see an a down here. It's actually an a squared, but that's okay. I can write it in as 4. And I see an a, so I'm going to replace it with a 2b. And it's squared, right? We also know we want to find an angle. So it might be handy to turn this a dot b thing into a dot product, which means it's a magnitude, and an angle. Okay. Oh, we got this equals 0 here. The first one, I need to expand this bracket. I need to square things. So I get 4b squared. I see this a thing here again, which we said previously that every time I see an a, I can replace it with a 2b. And it's got the other b there. Oops. Cos theta minus 3b squared. I know it looks like it's getting longer. It's actually going to get shorter in just a second. Okay. If I multiply these two things together, 4 times 4 makes 16b squared. 11 times 2b times b again makes 22b squared. Kind of handy here because now look, we're all doing in b squareds, right? Everything has a b squared attached to it. I can collect some like terms. Okay, these ones and these ones can go together. That'll make 13b squared plus 22b squared cos thetas. That equals 0. Okay, so I should be able to solve this. Now, how do I go about solving this? Well, what if I leave the b's on one side, the b cos theta on one side, and bring the 13 over to the other side? Our objective is to solve for the angle, right? So if I divide the left side by the 22b squared, it means I have to divide the right side by the 22b squared. And what's going to happen there? Well, we're left with cos theta equals, b's will cancel each other out. I'm left with negative 13 over 22. Something I can put in my calculator. Take the inverse of that negative value. Tells me I'm going to get an angle bigger than 90, and indeed I do. 126. And there's how we can sort of combine some algebraic expressions with dot products, with trigonometry, and produce a scalar value still.